So hello, thank you for coming. I'm Susanna, or am I Yoda? It seems I have features of both creatures. So open your participants pane, and towards the bottom of that, you can see some options for interacting. So please click on yes if you've seen Yoda in a Star Wars movie or know something about Yoda. I feel like there should be a lucky door prize for the first person to respond in the participant pane. Yes, we're seeing quite a few yeses here, which is great. There's also some people who haven't, so maybe they're deprived people who haven't seen Star Wars. But everyone with green against their name might realize that because I'm speaking in words of more than 2 syllables, and also my face isn't very green, I'm more likely to be Susanna. What if I showed you this map of a novel disease called ISO fever in a land far away, and you had to make some decisions? And just in case you think ISO fever doesn't sound like a very serious disease, it can lead to all kinds of side effects, so it should not be taken lightly. So with this map, you need to decide which areas have changed from high levels of cases in week 1 to low levels of cases in week 2. So how certain would you be that this area, which goes from red to deep green, has changed from high to low? In the participants pane, give me a thumbs up. This is under the more option if you're really confident it has, and a thumbs down if you're not confident it has. So we're seeing uncertainty here. So what about this area? So this goes from pale orange to pale green. So thumbs up if you're really confident it's changed from high to low, thumbs down if you're not confident. Majority suggesting not confident. So just in general, what kinds of things would you like to see changed about this map that would actually make it easier to understand? So you now have 1 minute to jot down as many points as you can, either on pen and paper or open notepad or something, about what you would change to help you interpret this map. And your time starts now. So I think the time's actually a bit stuck, so I might draw it to a close soon. Okay, so based on some work by Sue Bell and other people, some of the key features the map should include that they should be standalone. So what is it actually showing here? Is it incidence or prevalence? Counts or rates? What time frame is it actually showing? What year? Maybe what month? The second thing is, where is this? You might have wanted to see a location map showing the entire country and highlighting where this area comes from, maybe a scale bar, perhaps even a north arrow. And where did the data come from? How was it calculated? Was it modeled? The legend could definitely be more explicit. Values are relative to some kind of average measure. So what's the actual average that's comparing against? And the color scheme and values. So without knowing the values on the legend, it's really unclear if the color cut points are even appropriate. So my pet hate is maps that divide an area into quintiles and pay no attention that there might not be any variation across the areas. For example, the range of values might be from 0.99 to 1.02. You might not even like the choice of colors. Certainly the most prevalent form of color blindness does have difficulty distinguishing between red and greens. You might also consider whether it's photocopy friendly and other aspects. So this article by Bell mentions most of these points, but it also recommends testing map designs on your audience to try and gauge their understanding. You probably had other things listed as well, and there's a lot that would benefit from being altered here. In 2016, The Lancet published the guidelines for accurate and transparent health estimates reporting, which has the acronym GATHER. The GATHER statement included a checklist of 18 items that should be provided. Number 16 is to include uncertainty estimates. So as statisticians, we know the importance of uncertainty, yet often maps don't include any uncertainty around their estimates. Partly, this is because there's so much data already shown in this figure already. Maps often have hundreds or even thousands of estimates. But humans are really visual and we instinctively trust maps. So it's almost more important that for maps, we really emphasize there is uncertainty around the estimates. For the last decade, I've been mapping cancer data. So back in 2011, we released the Atlas of Cancer in Queensland report. More recently, in 2018, we released the Online Australian Cancer Atlas. Both of these have looked at small area variations in cancer incidence and survival. And one key feature of cancer is that it's one of the very few diseases in Australia where we have practically complete incidence data. So Australia has a lot of notifiable diseases, but many of these are known to be underreported. Consider, for example, COVID-19. It's a notifiable disease. It seems some people are largely asymptomatic, so they're not counted among the cases since they never get tested and diagnosed. But for cancer, by capturing all cases, we effectively have a census, not a sample. And occasionally, people have argued that therefore, measures of uncertainty are not even necessary, such as this letter published in a Swedish medical journal in 2004, which translation of the title is "Cancer researchers, please don't report on confidence intervals when it's not necessary." But as pointed out back in 1941, a census is really a sample if we're trying to generalize results and make decisions that need action. So it doesn't matter what your data source is, when mapping, we need to include the uncertainty around our estimates. Right at the start of the Australian Cancer Atlas project, we wanted to see what other maps had done, and Jessie Roberts led a review on cancer maps. She found that less than half included any measure of uncertainty, and the ones which did focused on showing it through graphs, rather than directly on the map. For instance, this is the online Missouri Cancer Registry maps. So take a good look. So let's capture your first impressions in a word cloud. So if you haven't yet opened a window at menti.com, you can go there now. And please enter the 6 digits shown at the top of this screen to enter your 3 words summarizing your first impressions. So the numbers are 18, 80, 22. That's 188022. I'll give you just a short time to enter your first impressions. So we're all entering lots of different words, but it seems there's not much favourable sentiment towards this map at the moment. I'll give you just a couple more minutes, well, not minutes, a couple more seconds to finish answering your 3 thoughts. We have a winner word now, busy. Certainly it's a very crowded, cluttered map, so I certainly agree with what people are expressing here. So the way this map actually, one good thing about it is that it does include the uncertainty measures, and it does that in 3 different ways. So firstly, it includes the uncertainty just in terms of the 95% confidence interval, and that appears when you hover over an area on the map. Then through this graph, the CIs are plotted, and you can compare the width to other areas for an overall snapshot of estimate precision. There's also another graph down the bottom, which at first glance appears to have nothing really to do with the uncertainty, but actually the purple triangles mean that it is significantly higher, and that appears when you hover over it, while the orange circles mean there's no difference. One thing I found a little bit disconcerting was that each cancer type had its own scale in this graph, so that the average is actually in the middle for every cancer type. So that means for this first row, which this area has a rate of about 519, it's actually further to the left than 3 or 4 rows down, where its rate's more around 100 or 66, but they're further to the right. However, it does nonetheless meet the gather statement. So another review that was led by Jesse Roberts mentioned 3 ways of mapping uncertainty. Whereas the previous one just had associated graphs, it didn't really have any visual thing. This is a way you can actually include it on the map. And so these approaches can use 2 different maps, or they can use the one map that shows both the estimates and the actual uncertainty. So the first approach, which uses 2 maps, is to have one map with the data and one map with the uncertainty. So this figure is mapping death rates. The first map shows the rates using a diverging color scheme. The second map shows which rates are considered to be reliable. This is just using a binary scheme of yes or no. Yes is colored dark gray, no is light gray. The binary classification does make the uncertainty map quite simple to interpret. A more complex display would be like this, where we have a range of values shown on both maps. So firstly, we have a bunch of different estimates with a diverging color scheme for odds ratios. And then on the other map, which is the uncertainty, it's a sequential color scheme. So in the participants pane, give a thumbs up if you like this way of representing it, thumbs down if you dislike having the 2 maps side by side. Some positive, quite a few negative. So the second option is we can actually combine the data and uncertainty as 2 separate components put into the one map. So this map has the uncertainty shown as a pattern on top of the mapped estimates. So in this example, when omega equals 0, we're very certain, but as it approaches 1, we become much less certain, and that pattern becomes much stronger until it partially obscures the data estimates. Again, this is kind of a continuous uncertainty scheme, so we could simplify, and here it just has like hatching saying, yes, it's not considered reliable, has no hatching, no considered reliable means it just has the same level of hatching. So in the participants pane, give a thumbs up if you like this way overall of having the one map with 2 separate components, thumbs down if you dislike. A lot more positive sentiments shown this time. Still potentially some negative. The There's many ways you might actually choose to incorporate the uncertainty when you're overlaying it on a map. So you might choose texture, as you just saw, or you might go for the sharpness with increasing fuzziness indicating uncertainty. Other common options include modifying the line width on the boundaries of areas. You can adjust the color saturation or hue, or add in transparency. But there's many, many possibilities. Now, when it comes to seamless integration, which is the third option, it most commonly uses color saturation. So this figure shows topsoil depth. The black dots indicate measurement locations. The rest of it is interpolated. So this particular map is how it would usually be represented. It just shows the estimate values. But a seamlessly integrated one with the uncertainty would have a two-dimensional legend where whiteness indicates uncertainty. So you can see how certain we are of results where the measurements were taken and how the estimates become more uncertain as we get further away. So thumbs up if you like this way of representing, thumbs down if you dislike. Probably mixed opinions, but yeah, certainly quite a few positive, but still some negative. So for the Australian Cancer Atlas, we wanted to show the uncertainty in a few ways, including incorporating it directly onto the map, but also keep it fairly simple and intuitive because a key target audience for us was people who didn't have much knowledge of statistics. Because the Australian Cancer Atlas used Bayesian estimates to obtain our results, we had the advantage of having a full posterior distribution for each estimate. So that means we can look at things like the posterior probabilities of being above a certain value. If anyone's unfamiliar with posterior probabilities, it's just the proportion of the posterior distribution that's above or below a certain value. So you can choose any value, but often one is chosen as the overall average. For this area, the posterior probability of being above 1 is 0.8, as 80% of the area is above 1. So initially we considered plotting the posterior probability of an estimate against its SIR. And SIR here means standardized incidence ratio. The SIR is shown on the x-axis and it has that diverging continuous color scheme from red to blue, and pale yellow represents the national average value. And the posterior probability here is shown on the y-axis. We do have slightly darker shading, it's fairly subtle, behind those with the posterior probability of being above 0.8 or below 0.2. And those cutoff values was determined by work from Richardson and others. But we really wanted to emphasize all the areas that we considered to be likely to differ from the national average. And so my colleague Earl Duncan invented the posterior probability differences. And it's the absolute difference between the posterior probability of an area's estimate being above 1 and below 1. So for our previous example, the posterior probability of being above 1 is 0.8. This also means that for this same area, the posterior probability of being below 1 is 0.2. So taking the absolute value of the difference, our posterior probability difference, or PPD, is 0.6, and we'd consider this area very likely to be above 1. And so we use these PPD values in 3 ways in the atlas. So first, we developed a new graph, which we called the V-plot. Can you guess why we called it a V-plot? These are our modeled SIR estimates on the x-axis and our posterior probability differences on the y-axis, which is labeled just probability. So this means that all the areas within the darker band at the top of our V-plot, which starts at 0.6, are considered likely to be different to the national average. And the estimates on the right within this band are likely to be above the average, estimates on the left likely to genuinely be below. Second way we used it was in a transparency overlay. So this is what we applied to the maps directly. So the color this overlay used was the same pale yellow as used for the national average. Opaque pale yellow had a PPD of 0. So those would be the areas that are shown right at the bottom of the V-plot. And at the top, it was the PPD of 1, and that was completely translucent in our overlay. So there was a continuous gradient between them. So this is using the second option we saw before of showing the uncertainty and the data on the one map, but as 2 separate components. So the defaults for the transparency overlay to be on, you can turn it off. Because we chose our color cut points quite carefully, it only makes a noticeable difference for the rarer cancers, which have more uncertainty around their estimates. So you can see how more vivid the colors here become when it's turned off, but having it on arguably allows for more accurate interpretation. And the third way that we use our posterior probability differences is literally just spelling out what it means by providing words. So when you click on a box, on an area, a box pops up, and you can see how it states it's likely to be a real difference. So that means it has a value above 0.6, and you can see how high it is on our B-plot. If we choose another cancer type, here it says it's unlikely to be a real difference, and on our V-plot, it's a lot lower down. But wait, there is more. So once an area is selected, you also have the opportunity to select the associated density plot. And on this plot, we have values for the 80% and 60% credible intervals, along with the median estimate. We also included some really nice features just to help people interact with the estimates. And we can filter on both our map and our V-plot by various categories or continuously for both estimates and for the uncertainty using the posterior probability differences. So if we select 1 and above, and then if we choose a probability of 0.6 and above, here called 60, then we'll only see the areas that are likely to be genuinely above the national average. And if we change our cancer type, the filters still remain in place. So if we then alter our diagnosis rate to include everything, we'll only see the areas that are considered to differ from the national average. And our V-plot also only includes those areas, and you can see that all estimates are within the darker background towards the top. We can also combine this with filtering by category, so here we could select just the remote areas, and it's the ones that differ from the national average. And we can choose to focus on specific values, so such as ones that are at least 10% above or below. And we do that by originally selecting the range between those values and then reversing our filter. So there's just heaps of options to interact with the data estimates and understand the uncertainty as well. But in addition to exploring interactively, you can also download all the modeled estimates used in the atlas by entering your email address under data download. And you then receive an email. It has the link. When you click on the link, it has downloaded results containing the modeled estimates for every cancer and sex combination in the atlas, for the 2,148 areas, for incidence and survival. So the measures of uncertainty included in the data download are the 80% and 95% credible intervals, as well as the posterior probability difference. And the downloaded folder contains 5 files. One's a README file. There are 2 Excel books, which are just nicely laid out for those who prefer to browse the results. And you can see each cancer has its own sheet in the Excel book. There's also sheets about summary data, some data and methods, and the geographical areas. But there's also 2 comma delimited files that have all the model estimates and are designed just to be read directly into statistical software. So we tried to cater to a range of audiences. So the atlas provides several ways of visualizing, interacting with, and using measures of uncertainty around the estimates. I do think the atlas is an amazing resource, and I'm not the only one. Just last week, it was an extreme honour for the Australian Cancer Atlas to receive 2 awards, including the most prestigious industry award bestowed by the Conveying and Spatial Sciences Institute, the Asia Pacific Spatial Excellence Award for Spatial Enablement, and the J.K. Barry Award for Overall Excellence. And we haven't actually yet received the trophies because it was done online, but the one shown is the one we received last year, which was just the Queensland Award for Spatial Enablement. But the certificate shown is the genuine real deal. So I do just want to acknowledge the hard work of the many amazing people who contributed to the Atlas project. The project was led by Professors Peter Barty and Kerry Mingerson, and we had a large multidisciplinary team, as well as the project advisory board. And they were just simply wonderful people to work with. It would also be remiss of me to not mention that the Atlas was a joint project between Cancer Council Queensland and QUT with support from Frontier SI. Funding and cancer data were obtained from AIHW and further support from 2 research centres of excellence. So there's really three things I'd like you to remember from my part of the talk. So firstly, including measures of uncertainty when mapping is really important. But secondly, it's less common to include the uncertainty directly on a map, but there's several ways this can be performed. And thirdly, the Australian Cancer Atlas showcases some ways, but always consider your audience's needs. As Yoda would say, try not, do or do not, there is no try. And to show you a really nice way to incorporate some of these techniques of including uncertainty into your map visualizations, please welcome Lydia, who will speak about her Vizumap R package. Thank you.
Okay, can everyone see that okay? All right, thanks, Susanna. My name is Lydia, and I'm going to be talking about the Vizumap R package today, which is a toolkit for visualizing uncertainty in spatial data. The package was created with Petra Kunert, and I would also like to recognize Chris Weichel. He's at the University of Missouri, and it was actually there that this project got started. And I would also like to recognize Sam Nelson. Sam is currently working on developing a Vizumap Shiny app, which is really exciting. Okay, so at the end of this talk, I'm going to have an audience poll in which you'll get to act as the decision maker and cast your vote on how you think it would be best to allocate resources given an uncertainty visualization. So if you could open up this link in another tab, that would be great. I think Jamie posted it in the chat, and then I'll post it again towards the end of the talk. So if you miss it now, don't worry. But you won't see anything there yet, but you'll be able to vote once I activate the question. Okay, I'm going to be talking about our motivating research problem, the 4 visualization methods in the Vizumap package, do a little demo on how to use Vizumap, and then also provide a sneak peek of the new Shiny app. Similar to Susanna, our motivating research problem was the issue of missing information on maps. Here I have screenshots from 2 government visualization tools, obviously not the Cancer Atlas, but in both cases, they're visualizing some type of statistic, but the uncertainty information is missing. You know, why is that a problem? Well, you know, it's an important piece of information that should be considered in the decision making. And you could include a table of all of these values. However, for something like the US, a US county map, that would include a table with 3,000 plus values. And so it's going to be very hard to get an overall idea of what the uncertainty is like. And it might even be ignored completely. For example, here, if you look just at this map without the captions, you're going to miss that for Los Angeles County, you have a margin of error of 0.1%, while for Kennedy County, Texas, you have a margin of error of 12.5%. So in addition to providing a crucial piece of information for decision makers, it can also highlight where data are lacking and where the model performs poorly, and therefore help direct future research. All right, Susanna did a nice job of covering a lot of the methods currently in the uncertainty visualization literature. But one thing that I noticed when reading through that is that there really is a general fear that adding this information to the map will clutter the map or make it difficult to interpret. And I think this is a very valid concern because there are only so many dimensions to a map, and it's a struggle to try and find ways to add another piece of information. I've seen people use hatch marks, patterns, fog, glyphs, transparency, resolution, and animation. Here's an example of fog in which people have overlaid fog on top of a contour map. And this approach sort of has some kind of some metaphorical value to it as well, in that, you know, fog, and it's representing areas that are unclear. Here's another example in which they've used the combination of color and texture to communicate both estimates and uncertainty. Okay, moving on to the 4 methods in Vizumap. They include the Bivariate choropleth map, map pixelation, glyph rotation, and the Exceedance probability map. The first 3 methods are discussed in that first paper, Visualizing Uncertainty in Aerial Data, and the 4th method is discussed in that second paper. For the Bivariate choropleth map, the approach is to average 2 single hue color palettes to get a bivariate color scheme. And from there, you can fill each region with a color that represents 2 values instead of 1. The method was introduced in the 1970s by the US Census Bureau, and at the time it was not well received. It was criticized heavily by statisticians and geographers, and I'll also note that it was used to visualize 2 variables instead of 1 variable and its uncertainty. Now, most of the criticism was centered around the construction of the bivariate color grid. So one criticism was that it had too many colors. It includes green, blue, orange, red, purple, basically every color of the rainbow. And another issue is that it was difficult to remember and not intuitive. And they actually did a study in which they cut the grid up into its 16 squares and then had participants try and put the grid back together. And they couldn't because the grid isn't intuitive. So we tried to make some improvements to the bivariate grid. The first is that we average RGB color codes and we limit it to just 2 colors. We use 9 squares instead of 16. And then we rotated the grid 45 degrees so that this top square here can either represent the highest in both categories or the lowest. Here's a summary of how we average the RGB components to get a new color. And here's an example map. So here we're visualizing the percentage of families whose income was below the poverty level in 2015. As you can see, for example, in this area where you've got the dark gray, that would represent the areas with the highest poverty rates, but also the most uncertainty. Throughout the Midwest, we have a lot of this yellow value, which would point to low poverty rates, but high uncertainty. And so this just offers a way to get both pieces of information on the map. All right, the second method, map pixelation. In this approach, we pixelate regions and then randomly assign each pixel a value within the estimate's margin of error. This method builds on 2 concepts in the uncertainty visualization literature. The first, that areas of high uncertainty can be represented by texture and noise. And then the second is that a masking approach can be best where you want to prevent users from making erroneous inferences. So in this method, you can't actually determine what the exact estimate and margin of error are. You just get a general idea. And for map pixelation, we have both static and dynamic maps. Here's a breakdown of how we fill each region. The estimate for this region is 21.4% and the margin of error is 4.1%. So we create a range on the color, that green color gradient, where the upper value of the range is the upper bound of the confidence interval and the lower value is the lower bound of the confidence interval. And then we sample from that range and fill the pixels. And so what happens is that you get areas of high uncertainty that appear pixelated because you might have one really dark green next to one light green. And then you get areas of low uncertainty that appear almost smooth because those green values filling the pixels are so similar. And you can choose what distribution you would like to sample from, whether that's a uniform or a normal distribution. It really just depends on what is most fitting for your map. Here's an example map visualizing poverty rates. So if you look around St. Louis, you'll see that those counties appear as if they're almost filled with only a single color. And that's just because there's low uncertainty there. And then in this region, in the southeast, it appears much more pixelated. And then we animated it so that the pixels flicker between sampled values. So here in that southeast region, you're going to see a lot of movement, whereas around St. Louis, it appears almost static, even though those pixels are moving just as fast. Moving on to glyph rotation, this method was inspired by the issue of varying region sizes on a choropleth map. Sometimes the smallest counties are the counties with the most people, and so we were trying to think of a method that would address that issue. We place a glyph of equal size at the centroid of each region, and then we fill the glyph with a color that represents the estimate, and we rotate the glyph depending on the error using that rotation matrix. And here's an example map of that. Another method in the Vizumap package is the exceedance probability map. Exceedance probabilities were highlighted in a paper by Petra Kunert and her colleagues as a useful tool for managers. You choose a threshold of concern, and then you plot the probability of exceeding that threshold of concern. You can easily calculate these from a posterior distribution of a Bayesian hierarchical model. And you do so by interrogating the posterior distribution, calculating the number of times each posterior draw exceeds the threshold, and then you divide the number of exceedances by the number of draws. And here's an example map of that. In this map, I'm plotting the predicted total suspended sediment concentrations in the upper Burdekin Catchment in Queensland, Australia. And this will be the example or the data that I use moving forward for the Vizumap demonstration. So you can download Vizumap from GitHub. And I would just like to acknowledge that Vizumap was built using the following R packages listed here. Like I said, you can install Vizumap from my GitHub repo, and included in the package download is a vignette that has a lot of examples and demonstrates in detail how you can use each of the Vizumap functions. There are three categories of Vizumap functions: formatting functions, building, and viewing functions. The formatting functions prepare your data and shapefile for use in the building functions. The building functions can be used to design your color palette, your map key, as well as your map. And then the viewing functions allow you to see the objects you've built, as well as combine them. So connect your key with your map. All right, so the first step, reading in data. For this example, I'm going to be using a data set that we've included in the Vizumap package, the upper Burdekin Catchment data. And I use that read.uv function to format for use in the building functions. You can also use this read.uv function to read in a CSV file. A little background on the data set. So it includes estimates of total suspended sediment concentrations, as well as the uncertainty for those predictions. You get sediment and catchment areas, and that can flood out into the Great Barrier Reef, causing issues. So we thought Vizumap would be an interesting way to produce visuals that have both the predictions and their uncertainty, and then use those to communicate to catchment managers and policymakers. All right, to build a palette, you use the build underscore palette function. You can one for pre-made palettes included in Vizumap, or you can use the build underscore palette function to try and write my own Bivariate color palette. So you can then build your Bivariate map using the build underscore bmap function. This syntax is the same throughout. So to build a pixel map, you'll use build underscore pmap. And to that function, I pass my data. The path that I've here, I decided to the Bivariate bins using terciles. Next, I attach the, or I build the Bivariate key. So I use build underscore b, pass in my palette, specify that I use terciles. And then I can use the attach underscore key function to connect my map and my key. So next, to create a pixel map, I first need to pixelate my shapefile. I can do that using the pixelate function, and then I can build my map using build underscore pmap. To this, I'll pass my data, the sampling distribution that I've chosen, my pixelated shapefile, I'll choose a color palette, and you get a map like this. Vizumap to animate that pixel map. To build a glyph map, I use build underscore gmap, and it's very similar. You're going to pass in your data, your shapefile, choose what type of glyph you'd like to use. We have two options, either this ice cream cone circle. And then similar to the Bivariate map, I need to build a key. And so I'll use build underscore g key, and then I can attach the two using attach underscore key. And finally, to build an exceedance map, I need to use the build underscore emap function. I pass in my data, my shapefile, and this data set includes pre-calculated exceedance probabilities. However, if you don't have that information, you can also specify a probability distribution function and the estimates and errors and pass that into the build emap function and create an exceedance probability map. All right, now it's your turn. So now you are the decision maker. And I'm going to activate the question, but you need to decide where you would like to target your remediation effort based on this visual here. So, oh, sorry. Oh, it's doing my, sorry, I accidentally skipped the slide. Once this is over, I will go back to my, visualization for the poll question. Let's see here, maybe if I go here. Okay, there it is. All right, so you can choose whether you would like to focus your efforts on the north, the east, the west, or the south. And we have both information about what the sediment prediction is, as well as what the error for that prediction is. Okay, so I can see that the South is consistently the most popular vote. So if we take a look at that again. So the South is really high predictions of TSS, but also a lot of uncertainty. So, you know, I think it's interesting when you incorporate the uncertainty into the decision-making process, all of a sudden it seems like it becomes much more of a balancing act. All right, moving on. I guess you got to already see this animation, but here is a sneak peek at the new Shiny app that Sam is creating. So you'll be able to choose your colors, plot on an actual map, and all 4 methods will be available in the app. Okay, future work. One thing we're interested in doing is exploring different map types. So maybe plotting these methods on, say, an equal area cartogram. Another thing that I think is really important to think about doing would be conducting user studies. So running experiments to see if these methods are effective and to try to better understand how people are interpreting uncertainty on the map. Also, it's always great to see new applications of the Vizumap methods. So if anyone creates a Vizumap map and wants to send it my way, I'd love that. And then also about we're working on getting a paper out, so watch for a Vizumap paper. And then here are a few references if you would like more information about methods. I just wanted to say thank you to SSA Queensland and Susanna for the invite to do a joint talk. And thanks everyone for tuning in.